car with a mass of 1.50 times 10 to the third kilograms starts from rest and accelerates to 18.0 meters per second in 12.0 seconds. Assume that air resistance remains constant at 400.0 newtons during this time. What is the average power developed by the engine?
So, we know the mass of the object, we know the initial velocity, we know the final velocity is 18 meters per second, we know it takes 12 seconds for that to occur, and the force of kinetic friction is 400 newtons. We're looking for the power developed by the engine. Now, whenever you're talking about power, just like work, you have to identify which specific force you are talking about. So when we say the power developed by the engine, which force specifically is it talking about? Bucker? What force is it that the engine is going to cause on the car?
Force applied.
That is going to be the force applied. So this is the power delivered by the force applied. Power delivered by the force applied is going to be equal to, we have two different equations we can choose from. Work over time, or we could do FV cosine theta. Which equation are you going to use and why? No.
You're going to want to use the first one because the velocities.
Notice we have velocities, right? But this velocity is changing. It's not a constant velocity. So we need to use the equation work due to the force applied divided by the time. So this is the force applied times the displacement times the cosine of theta divided by the time. Looking at that equation, we know the time. We do not know the force applied. We do not know the displacement. We do not know theta. Andrew, what do you want to do?
We could draw a free body diagram.
Okay, free body diagram. We have the car. We have wheels. We have our center of mass. Go ahead, Andrew.
We have the force of gravity going down. The force normal going up. The force of kinetic friction going to the left.
Thank you for being able to identify which direction my car was going.
And the force applied to the right.
We have our free body diagram. Adam, what now?
We should sum the forces.
Okay, pick a direction.
The y direction.
Go ahead.
The force normal minus the force of gravity equals mass times acceleration in the y direction. And mass times acceleration in the y direction equals 0. Acceleration in the y direction equals 0. Right, 0. So force normal minus the force of gravity equals 0. Subtract the force of gravity from both sides.
Can I add?
Yeah, add the force of and you get force normal plus the force of gravity. So force of gravity equals mg.
We now have the equation for the force normal. It is equal to mass times the acceleration due to gravity. I agree with that. True. We have drawn our free body diagram. We've listed what we're trying to find, which is the power delivered by the force applied. We've identified that we don't know the force applied, we don't know the displacement, we don't know theta. We've summed the forces in the y direction. What now, Victoria?
Sum them in the x direction.
Go ahead.
Force of kinetic, or negative force of kinetic friction plus force applied equals mass times acceleration in the x direction.
Okay. We now have negative force of kinetic friction plus the force applied equals mass times the acceleration in the x direction. George. George, we have people.
Okay, you guys plug in negative mu k times the force normal for the force of kinetic friction.
Negative mu k times the force normal plus the force applied equals mass times the acceleration in the x direction. Andrea?
Well, I don't think you need to substitute the k in force normal. or because you have the force of kinetic friction already?
We get so ingrained in the things that we know how to do and that we've done so many times, we forget what we know sometimes, right? We have the force of kinetic friction. George, do you see that we didn't need to substitute in UK times force home? This wasn't actually all that helpful. Stuart?
We use UAM on the acceleration.
We know the force of kinetic friction, 400. We know we're trying to find the force applied. We know the mass. We don't know the acceleration, so we could go through and use UAM to figure out the acceleration in the x direction. Did we need to sum the forces in the y direction? No. So notice we didn't even need to do this piece. Okay. All we needed was the sum of the forces in the x direction, and we can use UAM to figure out the acceleration in the x direction map.
Don't we not even need to use UAM?
Why not?
Because we have our change in velocity and our change in time.
Okay.
Just use that equation.
Go ahead.
Say our acceleration in the x direction is equal to change in velocity over change in time, which equals the velocity final minus velocity initial over the change in time.
Let me just do this for you. I agree with everything you've done so far. Let me just do one thing. If I multiply both sides by delta t, I get the acceleration in the x direction times delta t equals velocity final minus velocity initial. If I add velocity initial to both sides, I get the velocity initial plus the acceleration in the x direction times delta t equals velocity final. Or if you prefer, velocity final equals velocity initial plus the acceleration in the x direction times delta t. Right? So notice it's actually the same thing.
Okay.
So this equation, the definition of acceleration, is one of the UAM equations. It's just rearranged. So either way, it's the same thing. So the acceleration in the x direction is equal to the final velocity, which is 18, minus the initial velocity, which is 0, divided by the total time, which is 12. So the acceleration in the x direction equals 1.5 meters per second squared. Great, we figured out the acceleration in the x direction. How are we going to use that? Eric?
Well, once you found acceleration in the x direction, you can apply. Wait.
It's not there. It's all up here and in your brain. That's okay. Nate's gonna help you out.
We can solve the sum of the force in the x direction through force applied now.
We need the force applied because it's in the power equation, and we can solve for this equation with the force applied. So the force applied equals mass times the acceleration in the x direction plus the force of kinetic friction. The mass, I believe, was 1,500. The acceleration in the x direction, we just got to be 1.5 plus the force of kinetic friction was 400. The force applied then equals 2,650 newtons. We have the force applied. We need the displacement and we need theta. Ian. We figured out force applied, we have time, we need the displacement and theta.
Isn't theta 180?
Isn't theta 180? That's in your work due to the force of friction equation. You got to be careful. That's only in the work due to the force of friction equation. Julia, you want to help out?
Is theta 0?
Is theta 0? Class point in the direction of the force applied. Use the other hand to point in the direction of the displacement. What's the angle between your two hands? 0. So yes. So notice then we have theta is equal to 0. I'll write that down a little bit once we figure out our displacement. We're close. We only need our displacement. Eric?
Can you use a UAM?
We can.
Velocity final squared equals velocity initial squared plus 2 times acceleration and that displacement.
I'm just going to put x's just to identify everything's in the x direction. Final velocity in the x direction. We have that is the initial velocity that is 0. So bless you, the initial velocity is equal to 0. We're looking for delta x. So delta x equals the velocity final in the x direction squared divided by 2 times the acceleration. Velocity final is 18, which we're going to square divided by 2 times the acceleration, which is 1.5. What is our displacement, please?
6 meters?
Say again?
6 meters? No, wait.
109.
Did you forget the square? Okay, so we have, oh, I don't need a box there. 108 meters, we are very close. We now have the force applied, which was 2,650 newtons. The displacement we just got to be 108. We figured out that the angle is 0 degrees, and we know the time is 12 seconds. 23,850 watts. You guys are less familiar with watts and more familiar with horses, so let's convert 746 watts on the bottom, 1 horsepower on the top. Watts cancel out, we get
31.9705 horsepower.
with sig figs 32.0 horsepower. 32 horses under the hood. Is that a large number of horses or a low number of horses? Really, if you were to take 32 horses and strap them to the front of the car and go, yeah, you would think that's a small number of horses. Yeah! Right, that's what it means. Basically what we're saying here is, if you take 32 standard horses, strap them to the front of the vehicle, and ask them to giddy up, this is what would happen. With respect to a car, however, this is not that many horses, right? The horsepower of an engine, generally this is not. So let's discuss what's going on here. We're going from an initial velocity of 0 to a final velocity of 18 meters per second in 12 seconds. Let's convert this final velocity so you can have some concept of what's going on here. We have 18.0 meters per second. That is 3,600 seconds on the top, 1 hour on the bottom, because there are 3,600 seconds in an hour. And here we have 1,609 meters in every mile. So meters cancel out. What is the final velocity in miles per hour? 40.273 with sig figs, 40.3 miles per hour. This right here is going from 0 to 40 miles an hour in 12 seconds. Yes. Ladies and gentlemen, people, this is how Mr. Palmer drives. Oh yeah. Here you go, you ready? When you put your foot on the horse pedal, you get to decide how many horses are going to be in front of your vehicle. Basically, at the front you have a reservoir of horses that you can just pull out. Push the foot down a little bit farther, you get more horses. Now, I don't know if you knew this, but horses eat hay. Hay costs money. So whenever you put your foot just a little bit further down on that horse pedal, you have more horses, more hay, more money that it costs you. In addition to this, horses that eat hay digest hay, and then it comes out the other end as horse poop. So the further you put your foot down on the horse pedal, the more money it costs you, and the more horse poop we have on the road. I don't know if you've seen it, it gets off the road, it gets kind of ugly, it gets all over the planet. I don't know if you've noticed that. Now, sometimes you guys pass me by when I'm using 32 horses. And I watch you pass by. And I just say, it's okay, I'm saving hay. Oh yeah, I'm so proud of that. 1973, oil crisis. National oil crisis. 1974, the US government passes a national safety, or a national speed limit on the highways. Anybody know what that speed limit was? 55 miles per hour. Who can tell me why they chose 55 miles per hour? Because it's the most efficient speed you can drive your car at. 55 miles per hour. For every mile per hour you go above 55 miles per hour, the efficiency of your vehicle actually goes down. It just continues to go down. So the farther you put your foot down on that horse pedal, the more money, the more hay, the more horse poop. It was a national crisis. And the idea was that we could save oil by decreasing the speed that people drove at. It was actually not very effective because people largely ignored the speed limit, including the people who were supposed to be enforcing the speed limit. In the mid-'80s, I believe 86, 87, it was increased to 65, and in 1995 they actually repealed that limit. So think about that. It was a way to fight an oil crisis, to increase the efficiency of the vehicles. Wouldn't that be nice?